Okay, so I want to do a video that just has some of the review of what the key learning from this week. But before I do that, I was at a wedding right before this shutdown stuff happened, and they were playing Ave Maria. So I want to learn to play Ave Maria on the harmonica. So I'm just starting, but let's see how this goes. Anyway, it goes on from there. Looks like I got some work to do for spring break. Get a little better at that. So let's do let's kind of review now. And so I want to, what is the learning from this week? Aqueous solutions and molarity. So I'm going to do just a quick kind of go through all of those things. And then we'll see what we can get done after spring break. So, and hopefully you guys are going to be practicing, learning some new skills of other non-school stuff, like me on the harmonica okay. Let's look at water. So we want to talk about water as polar. That was part of it, right? Water is this polar molecule that allows it to dissolve things like ionic compounds. Oxygen, I've drawn just part of this of this corner of the periodic table. Helium's up there in the top. Oxygen's right here, which is important because it's got an atomic number of 8 protons in the nucleus. Its first layer has 2 electrons, 1, 2, and the second shell, its valence shell, has 6. 1, 2, 3, 4, 5, 6. Well, this arrangement makes oxygen one of the few atoms that pulls the most. The only one atom that pulls electrons in tighter and closer to it would be fluorine. So oxygen really pulls those electrons in. So it's got the +8 charge, only 2 shielding electrons, so +6. So these 6 electrons really get pulled in. Looking at the Lewis structure for oxygen, there's its 6 electrons. It needs a full shell of 8 to be energy favorable. So it's going to find a hydrogen like this, bond with the hydrogen, and then bond with another hydrogen to do that. Now it has, through sharing with 2 hydrogens, it has its full shell of 8. Well, if that was the actual shape of water, and it was just like this, it wouldn't really be what we say a polar molecule. There's not like, the electrons are kind of in the center. They're not off to one side. But that's not the shape of oxygen. These 4 little regions around it, there's a pair here, pair here, pair here, pair here. Those 4 areas where there's a pair of electrons that want to get as far away from each other as they can. And grabbing my models here. So they get as far away from each other as they can. So what they'll actually do is they won't be shaped in this kind of linear fashion like this. To get away here, we call it a tetrahedral structure. So the hydrogens are going to be sticking out here, and these unpaired electrons taking up their own space. So it kind of looks like this. So I see that the hydrogens are here, and the oxygen, actually, that big electron puller, is on one side. We'll usually simplify like this and show the water molecule like this. So it has one side where there's electrons, and the other side is the hydrogen that doesn't see as much of those electrons. So to redraw, it might be a little more informative to show it something more like this. There's the shared ones. So the hydrogens are off on one side, the oxygen's up on the other side. So this side has a lot of electrons. It tends to be kind of negative-ish, or there's the lopsided negative charge in this neutral molecule is on one side, and the other side's positive. What that allows water to do is it can attach itself to ions. So if I add a solid into my water, or if I, take a solid and add some water or something, so that how does it dissolve? So an ion would be like this, plus, minus, an ionic compound, like that. Well, the water can come in and attach. The positive side of water can come in here, that would be this, HOH, and attach itself to the negative ion. The positive ion would be attracted to the negative side of water, which is the oxygen side. So that's a very strong attractive force between water and ions. And so they will actually surround these, break them apart, and then put them in solution. A positive ion will wind up being surrounded by several waters, etc. The negative ion will be surrounded by several waters, orienting themselves so that the positive side of water is attached to the negative ion. And that allows these ionic compounds to dissolve easily in water. This is an energy thing. I'm not going to get into that now. So what am I doing? I'm breaking some bonds, right? I'm breaking these ionic bonds, breaking those. And I'm making bonds. I'm making these attractions between the ions and water. We'll do the energy part some other time. Okay, so from there, we got into concentration. So we got into concentration. And the concentration, the way we measure, so how much stuff is there, and the stuff inside, whatever's absorbed in the water, is called the solute, and the water itself that's doing the absorbing is called the solvent. So we say, well, how concentrated is it? Concentration. And the way we measure concentration, usually, there's other ways, but the most common way is in how many moles of solute per liter of solution. That's how we measure it, right? Quantity in chemistry, quantity is in moles, and then volume, in this case, in liters. I can do this way, moles per volume, as long as my volume is in liters, equals big capital M for molarity. And so let's use that. So let's say I take 0.25. I'm going to take 50 milliliters, and I'm going to add 0.25 moles of salt, sodium chloride. And I want to say, well, how concentrated is that? And we're going to use this, the moles divided by the volume in liters. We call that the concentration or the molarity. So let's change this first of all. I've given you the volume in milliliters, which is how we'd normally say if I have a small volume like this. But for our equation, we need liters. 50 milliliters. There's 1,000 milliliters in a liter. 1, 2, 3. 0.050 liters. So the concentration equals the moles. I added 0.25 moles. Divided by the volume, as long as I've changed my volume to liters. And if you divide that out, it comes out to 5.0 moles per liter, or molar. So it's a 5 molar solution. That's pretty concentrated. That's very salty salt water. So that's a very concentrated solution of salt water. So this is how we could do it. Of course, it could be a two-step problem. I could have given you, just to keep the video shorter, I gave it to you in moles. I could give it to you in grams, at a certain number of grams. This would be about 15 grams of salt. And then you would have to step 1, convert it to moles, and then moles into volume. Now the other thing we did is say, well, that's super salty, 5.0 molar. That would be the equivalent, if I had a whole liter of solution, having 5 moles of salt in a liter of solution. So then we did the other one. We say, let's arrange this molarity equation. To find the moles. So I'm going to multiply both sides by V. Moles equals concentration times volume. So let's say I'm going to take this 50 milliliters of super salty water and I want to make it a lot less salty. So I'm gonna redraw it here. Here's my 50 milliliters. I left the dot off. I got to dilute this down. That's too salty for me. So what I'm going to do is I'm going to add 200 milliliters of water. So I'm going to dilute this thing down. And now we're going to use our equation that I developed in the other video. And that says all the moles, if I dilute that, all the moles of salt came from my initial little concentrated salt water. So I haven't given you directly this volume, so I chose this example so that we do that together. Let's figure out what I got. So after adding 200 milliliters of water to my 50 milliliters of my concentrated salt water, my volume of diluted, after dilution, 200 milliliters of water plus the 50 milliliters I started with equals 250 milliliters. Let's turn that into liters. 1, 2, 3. 0.25 liters. The molarity of my diluted solution is, I don't know. That's what we're going to find out. I've got all my information for the concentrate. The molarity of the concentrated, we had just found that was 5.0 moles per liter in that little 50 milliliter sample. The volume of the concentrate is 50 milliliters, which is 0.050 liters. Let's plug that into this equation and solve. Dropping units momentarily, times 0.050 equals molarity diluted times 0.25. So we'll divide that. This is going to be, it's now 5 times the volume. So I made my volume, I just did that, the math in my head. Hopefully I did that right. I made the volume went up 5 times. So if you multiply that all out, I'm pretty sure you'll get it's 1.0 molar. And so that's some of that. So I'm giving you just a few problems to practice. We're into spring break. And then we'll see what happens, because I don't think school's going to be back in session regular-wise when we're out of spring break. We'll see what happens. Enjoy your spring break.